Hi everyone, my name is Alex Schettelbauer. Today we're going to explore modeling with the Constructive Solid Geometry Library. So a quick overview of today's talk. We're going to start by going over types of modeling, because there's different ways to model 3D objects, and then depending on how I want to use them, we'll want to use different kind of methods of modeling. And we'll also use that kind of motivate why we decided to focus on constructive solid geometry as kind of our main modeling kind of method here. After that, we'll go over the geometric models Packlet, which is a new Packlet we're going to be adding here that helps with the modeling. And then we'll give a brief demo of that, and then we'll end things off with any questions that you may have. So if you have any questions or any talk, please put them in the Q&A tab, and I'll try to get to them at the end. All right, with that said, let's get started. So types of modeling. So there are many ways to model a 3D object, and the best method is going to depend on what you want to use that object for. So for example, you can do rendering, you might want to do some simulation and computation on it. You may want to make it a real-world object by either 3D printing or manufacturing it. Depending on what you want to use it for, that'll determine both what we model and how we represent it. So as far as what we model, the first option here is going to be surface modeling. So here, as the name implies, we only model the object's surface. We tend to do this when we only want to render the object, since in that case, we really only care about the surface data. So this is kind of one of the most common ways you see models. It's used in animation, video games, and other visualizations. However, it does have some drawbacks. The main one being that it's missing that clearly defined interior, which is usually vital for things like computations or manufacturing. For example, if you want to solve like an integral over a volume, you need to know what that volume actually is. So in some cases, you may be able to process a surface model into a solid representation. However, there are no guarantees. There can be all sorts of issues with the mesh that might call things that make it non-manifold. And here are just some examples listed here. For example, there can be holes, overlapping faces, singular edges, things like that that make it hard to process and figure out what exactly is the interior of the shape. So the solution then is to not model the surface, but to model the solid. So in solid modeling, we model the interior or the volume of the object. And usually in this case, the surface can be implied from that solid. This is useful for simulations and manufacturing since we now have that well-defined interior, and we can typically still render it fairly easily. However, when it comes to kind of solid modeling, there are different ways to actually represent the underlying data. So here are the three most common ways. The first one we have here on the left is the boundary representation, or the BREP. This is pretty similar to surface modeling, where we just model the boundary surface. However, it does have to be essentially a nice closed manifold mesh. So it can be a little trickier to actually specify this mesh. It has to meet certain constraints. In Wolfram Language, this is represented by the boundary mesh region. So you can create it through that. Next up here in the middle, we have a solid mesh. This is a mesh where it consists of solid cells. So instead of having, for example, like polygon cells, like triangles, it has 3D cells like the tetrahedron here. And since all the cells are solids, the mesh as a whole is solid. In Wolfram Language, you can represent this as a mesh region with polyhedrons as its mesh cells. And lastly here on the right, we have constructed solid geometry. This is a model defined by applying Boolean operations to primitive regions. And we'll see more about that in a bit. But first, let's discuss these first two. So both the BREPs and solid meshes are examples of explicit modeling. This is modeling where we define the models by their geometry alone, often, for example, vertices, edges, or faces, which are then directly edited by the user. So for example, a lot of applications like Blender or Maya, you'll create your 3D model by selecting, adding, or modifying vertices, edges, and faces. Now, there are some drawbacks to this. One, like I just mentioned, you usually need some sort of visual editor, and those can be pretty complex and involved. And they can take a while to learn as well. Next, it can be difficult to change an existing model. So often once you make a model, you can only make some minor tweaks to it. You can't drastically change the shape because you have to change all the vertices and edges, which can be difficult to do. Kind of related to that as well is discretization accuracy. So when you make those models, they are now kind of discrete with a certain resolution, and it's hard to kind of get more resolution after the fact. So you're kind of stuck with whatever accuracy you have initially. And lastly, they tend to require more memory because you have a lot of different cells, whether it be triangles or tetrahedrons, that can take up a lot of space, especially for large complex models. So kind of the solution to all these is parametric modeling. So in parametric modeling, we basically have the true or original model, which is defined by some either equation or some other kind of structure. And then we can adjust its parameters and regenerate it whenever we want. This makes it really easy to modify or iterate on existing models. You're no longer like locked into that final version. It's also, if you need to convert it to one of those discretized models, you can, and you can decide what accuracy you need at the time of discretization. And lastly, we can still render it fairly quickly usually. So kind of the recap here we discussed. So we want a modeling system that is one, solid first. So models have to have a guaranteed volume so that they can work well, not just with rendering, but with other things like simulations and manufacturing. We also want them to be parametric, so they're easy to modify. We don't have to worry about vertices or edges, or even using like a separate software to do that. We want them to be fast to render, so we can quickly see changes as we make them. We want it to be code first, so we don't need that editor. We can just, for example, in a mathematica notebook, just create the model through that. And lastly, we didn't discuss this, but we'd also like it to be intuitive. So instead of kind of dealing with vertices and edges, it'd be much nicer if we could do something like in the real world where we sculpt or machine an object by adding or removing kind of volume to it. So for all these reasons, we have chosen constructive solid geometry as our kind of main modeling method here. So constructive solid geometry, this is a technique for creating 3D models by combining primitive regions through Boolean operations. And those are 3 different operations here. We have union, intersection, and difference. Now CSG forms a tree structure where at the very bottom here, you're going to have your primitive regions as leaf nodes. And every internal node is essentially a Boolean operation on its child nodes. So for example, here we have the intersection of the sphere and this cube to get this region here. And you just work your way up that tree until the root node is your final model. And in Wolfram Language, you can represent these with the CSGRegion symbol. Now the CSGRegion here, you specify it by giving the operation here as a string, and then you can give the child regions and a list after it. So here we have the intersection of that cube and a ball to get this shape. We can also nest CSGRegions. So here we have a nested one that's kind of uses a lot of different primitives merged together. And we can take a look at its tree. So here's the kind of underlying representation of that model. So we still have all these primitives, and we can kind of, after the fact, we could change these if we wanted to adjust the model. And then here are just some more neat examples. For example, we have hollowing out a polyhedron and applying colors to it. And we also have kind of taking an object, in this case a ball, and kind of splitting it into 8 sectors and then kind of separating those apart. Now, both of these would be pretty tricky to do with traditional explicit modeling. For example, if you wanted to specify all the vertices in a mesh region or boundary mesh region, that'd be pretty tough to do just through code. But with CSGRegion, it's fairly easy to do. All right, so CSGRegion has been around for a few years now, and we're continuing to try to improve it. For example, in the upcoming 14.2 release, we're bringing full annotation support to CSGRegion. So this means we can do stuff like adding annotations to any of the nodes in the CSGRegion tree. So in this case, we can add a style to the ball and add a kind of custom annotation here. In this case, it's material with metal. We can evaluate that, and we see it's added that styling to the ball. I can use annotate to add a style to that first child node here, this cube, and set its style to be blue after the fact like this. And we can also query it for annotation values. In this case, I want to check what that material was on the first child node. And we can see it was metal. It's just a quick view, but there's kind of the full list here of the now supported annotation symbols. Anyway, getting back to modeling. So while it's easier to model kind of regions using CSGRegion, it can still be difficult to make complex models using just the basic primitives like cylinders, cubes, and balls. So what we want to do instead is have access to a library of CSG parts that we could then assemble to make more complex models, so you don't have to start from scratch each time. This is the goal of the new geometric models packlet. All right, so geometric models packlet. This packlet is meant to provide a list of parameterized parts to help with the creation of these complex models with a real focus on mechanical and industrial design. This packlet will be available from the packlet repository under the name Wolfram/geometric models. As far as what's in this packlet, will basically be different part libraries. So our goal is to kind of take existing part libraries that are out there that have these nice parameterized parts and convert them into our format of CSGRegion and make them easy to use. So our strategy so far has been looking at libraries that are accessible through this open source software called OpenSCAD, which is a kind of constructed solid modeling software. The two we have been working with so far are the bolts library and the NopeSCAD library. The bolts library is just a free open source parts library for CAD applications. It includes parts like screws, washers, bearings, kind of things that you find at a hardware store. And like a hardware store, it contains a lot of different sort of standard presets for these. So you might have, for example, one model might be a hex screw, but it has a lot of different sizes and real-world units that you might find if you're going through bins at a hardware store. Next one here, we just started adding this one, but this will be the NopeSCAD library, which is contains different parts for stuff like 3D printing, electronics, and other related things like enclosures. So we'll see some of those here. All right, so finally we have the demo here. So for this demo, we'll quickly go over how to use geometric models in its current form. So quick disclaimer, this packlet is still in active development and everything I show here is subject to change. Particularly the typesetting and naming are not finalized. So what you see will probably look a little different in the final product. And last note here, the current design is loosely based on system model. So if you've seen that symbol, this might look familiar to you. All right, so first up with the new geometric model symbol that's available from the geometric models packlet. In order to actually reference a model, you can give it its fully qualified name. Here we start with the kind of library we source it from, the category, and the name of the actual model. So we can just evaluate that. And we see we have this little box here that represents our model. Instead of using this full qualified name, we could just use the final base name if it's unique. So it saves a little time there. So we just have this nice little fan blower. And lastly, if you want to kind of search to see what parts are available, you can use this asterisk notation where we give the string path you want and then put the asterisk star, and it will find any matching names that match with that. So in this case, we're looking up all the different washer models in the bolts library. All right, so once we have our model, example, this washer here, we can then look at its properties. So we can just do this bracket notation with the property string inside and evaluate that to get the properties. So this one just returns all the available properties we have on this current model. We can see stuff like the summary, which gives us some basic info, a description, what standards it supports, and so on. We can also, for example, get the graphics object if you want to view that, and more importantly, the region. So this is the kind of region here, and this is an actual CSG region, as I mentioned before. And since it's a CSG region, we can then kind of look at its underlying structure of the tree and see the primitives that it's made of. All right, next up is parameters. So we have a model, we want to be able to customize it. We do that through parameters. So if we look at this parameters property, we can see kind of a summary table here of all the parameters with their names on the left here. We can see they have different types like length or color. For stuff like length, we'll also have units, and it'll have stuff like the default value, current value, and a short description. In order to set these parameters, you can just pass in basically an override here. So I want to use that LED model, but I want to override this color parameter to be green instead of red. And evaluate that, and we see now it's green. Also note that these parameters respect units. So by default, if you just pass in a number with no unit attached, it will assume it's the default unit of that parameter. However, if we do something like pass in a quantity with a quantity unit on it, it will respect those and convert them as necessary. So here we have, they're both 2, the millimeters versus centimeters. We can see the difference there on the height. All right, next is parameter presets. So often we don't want to manually set the parameters ourselves, but we want to choose from some kind of pre-existing parameter presets for the model. For things like the bolts library, this is often the different standard values, so like different size screws or bolt nuts. But in this case, we'll have different LED sizes. So we can see we get the name of the preset on the left here with all the values for that preset on the right. And then we can either paste in these values directly, or we can just paste in the name as that second argument here, geometric model, evaluate it, and we can see we get the 8mm LED here, which is much bigger. And here we can just quickly render all the presets and kind of see how you can change the model just through the parameters without actually changing the underlying specification of the model itself. All right. And kind of lastly here, this is still something we're working on. But what we plan to add here is a way to combine models to form new composite models. So like I mentioned before, instead of combining just simple primitive regions, we want to be able to combine these actual more complex models so it's easier to build things as a user. So this isn't currently implemented in Attackle yet, but kind of a rough idea of what would be happening would be we, for example, take these 3 different models here, where we have kind of the screw, hex bolt nut, and then a washer. We can then take those and combine them all into a single region, which you can see here. And then we can take that region, kind of multiply it a few times, and then add it to a base board. And when we do that, we see we now have this more complex region with the different screws attached to this board. You see the back here. And so this is what we mean when we say we want to have more composite models. We want to be able to quickly use these to build up models, almost like you're assembling a part in real life. All right. So kind of the sum up here. So there is still remaining work here, as you've probably seen. One, like I just mentioned, we had that mechanism for model composition we're still working on. That'll be very important to this. Next, we want to be able to support more part libraries and also continue to import kind of new parts from those 2 libraries I mentioned, just so we have a wider array of things available to users that you can choose from. And lastly, just general refinement and polish, just finalizing the design and making it look nice and be easy to work with. All right, that concludes the bulk of my talk. So now if you have any questions, you can type them in the Q&A tab and I'll try to answer them here. All right, first question I see here from David. Can the 3 types of models be combined, i.e. BREP, solid, and CSG? So currently you can't directly combine them. For example, in CSG, you have to kind of just give it the existing primitives that it accepts. However, that's something you want to extend, so you could just be able to pass in, for example, like a solid mesh or a BREP, and just have it automatically break that down. For example, a solid mesh of tetrahedrons, we could just represent that as a union of tetrahedrons, which would be a valid CSG region. And for a BREP, you could always kind of discretize it and separate it into solid objects as well, since it's a well-defined solid there. So would be possible, but not currently supported. Though you could sort of manually decompose them yourself to make a CSG region. But yeah, it's a good question. That's something we do want to add, so it's much easier to kind of switch between these different representations. All right, another question from Wolfgang. Is there also support for BSP trees, or are they already working under the hood? I believe that internally there are BSP trees for certain Boolean operations. I don't think we yet have any surfaced API for working with them though. but I'm not positive on that. All right, next question also from David. Is there support for docking, such as bringing a cylinder towards a cube until they touch? Not yet. This is something where we will want to add sort of a suite of different operations to CSGRegion to make modeling easier. And one of those is like very common in these different modeling softwares is like alignment. So if you want to have things perfectly aligned without messing with the numbers yourself, that is a very nice feature, which we also like to add as well. All right, another question from Andreas. What can I do with these objects afterwards? Like send them to a printer and how? Yeah, so once you have a CSGRegion, you can always, for example, discretize it into a mesh or boundary mesh region and send those to a printer or do computations on those directly. We're also kind of working on making that step a little shorter. So by default, if we can't compute directly on a CSGRegion, have that conversion happen behind the scenes automatically. They're not sure currently an existing version if that's in there. But yeah, so ideally it works on CSG directly, or worst case, if it doesn't, it'll fall back to the either boundary mesh or mesh region. Then it can do either computation or printing with that. All right, another question from Jeffrey. Any plans to support solid geometry properties with varying values like density? Currently, no. I feel like right now they'd probably add a lot of complexity to it. But it's a good idea to consider in the future. All right, another question from David. Can a 3D region be specified from multiple 2D views of the 3D region from different viewpoints? So assuming you have like a front on, top down, or like side view. I don't believe we have an existing way to automatically generate a shape from that. But I've written code that does something similar in the past. For example, you could use like image 3D and then project those views if it's like a binary yes or no for the region and sort of carve out the image 3D from each of those sides. And then you could run something like image mesh to convert that image 3D into a mesh region. Yeah, so that's possible, but yeah, not, I don't think there's any built-in kind of workflow for that currently. All right, another question. Can OpenSCAD model be imported? And can we export to OpenSCAD? Sort of. So right now, it's just internal. It's not surface, but it's something we could allow access to. But for OpenSCAD, they have their main sort of format that's basically like its own coding language. But they also have their own kind of custom CSG format, which is kind of like the almost like compiled version of that, which is just kind of describing the actual object. So there's no like for loops or variables. And that's pretty close to what we have for CSGRegion. So I have written an importer for that internally, where you can take that kind of compiled version of OpenSCAD model and bring it into a Wolfram language. And then I don't think we have anything currently to export to OpenSCAD, but it wouldn't be too difficult to do that as well. So it's something, yeah, I should consider exposing that in the Packlet as well. Yeah, good question. Question from Tim here. Any plans to deform an object? I wonder if by deform you mean sort of either like bones or I've seen like the cage deformations before, where you can kind of wrap a cage around something and squish it by squishing the corners. As far as I know, no plans for that currently. There is certain things we're planning to add to it, such as extrusions, including the ability to like have a 2D shape and then extrude it vertically and then do like a twist on it and different things like that. So that sort of could be seen as like deformation. Yeah, so depending on what you mean by deformation, maybe. All right, another question here. Can point cloud data be imported to create a 3D model? Yes, we have a few different functions for converting what could be like point data into like 3D region. recall, I think we have reconstruction mesh is one of the main ones here, but there's also stuff like gradient fitted mesh. And if it is a convex object, you always have a convex hole mesh as well. So these ones can take point clouds and they'll try to return a 3D mesh of it. And for example, like reconstruction mesh has a few different options for the method it uses for that. There's like a concave hole mesh and like Poisson mesh. So yeah, there are ways to do it, and you might have to kind of try different methods to find one that works best. Also, I just wanted to go back to the question about deformation. I also just want to call out in case you also think about transformations. So any of these shapes and primitives, you can freely apply any affine transformation. So any scaling, rotation, or translation, you can apply all those in CSGRegion and it'll just work. So you can deform things that way as well. All right, I think our time's up now and the questions are slowing down. So once again, thank you for coming to this talk. And there are a few other geometry talks this conference, so stay tuned for those. And yeah, hope you have a good rest of your conference. Thanks. Bye.